into the world of quarks and dark matter. Buckle up because we're going from the tiny particles that make up everything we see to the invisible stuff that holds galaxies together.
It really is amazing to think that something we can't even see could have such a profound impact on the universe as a whole.
Right, it's like a cosmic puzzle. And we're going to use the excerpts he sent us as our guide. We're talking about articles that explore the relationship between quarks and dark matter. And they get pretty mind-bending as we go. But before we get lost in the theoretical weeds, let's start with a quick refresher. Most of us know about atoms, and that atoms are made of protons, neutrons, and electrons. But what are protons and neutrons actually made of?
Well, that's where quarks come in. They're these tiny particles, and physicists have identified 6 different types, or flavors as they call them: up, down, charm, strange, top, and bottom.
6 flavors of quarks. It's like a cosmic ice cream shop. So how do these quarks actually make up the protons and neutrons that we're familiar with?
It's all about combinations. Think of it like building with Legos. A proton is made of 2 up quarks and 1 down quark, all stuck together.
Okay. And what's the glue that holds these quarks together?
That would be the strong nuclear force, one of the 4 fundamental forces of nature. And it's carried by particles called gluons. Gluons are like tiny messengers that constantly zip back and forth between the quarks, binding them together incredibly tightly.
So we've got these tiny but mighty quarks making up the stuff we see and touch every day. But then there's this whole other kind of matter, dark matter, that we can't see or touch. If it's invisible, how do we even know it exists?
We can see its effects. Think of it like this. Imagine you see a bunch of leaves swirling around, as if caught in a whirlwind. But you can't see the wind itself. That's kind of what's happening with dark matter. We can see its gravitational pull on stars and galaxies. Things are moving in ways they shouldn't if only the matter we see was there.
So like a cosmic ghost, influencing things but staying hidden? And this ghost makes up a pretty big chunk of the universe, right?
A huge chunk. Astronomers estimate that dark matter makes up about 25% of the universe's total mass and energy. That's 5 times more than the regular matter we're made of.
Wow. Okay, so we know dark matter's out there, but we don't know what it is. And that's where the fun begins, right? Because your excerpts actually explore a bunch of really fascinating theories that try to connect this mysterious dark matter to the familiar world of quarks.
Absolutely. There's a whole spectrum of ideas, some more mainstream, others pushing the boundaries of what we think is possible.
Okay, let's dive into some of these theories. One that caught my eye was the idea of Quark Nuggets. What are those?
Imagine taking all the quarks in a galaxy and squeezing them into a space the size of a small asteroid. That's a quark nugget. Incredibly dense, stable objects made entirely of quarks and gluons.
So like a super concentrated quark smoothie. And the theory is that these nuggets could be dark matter.
Exactly. Because of their extreme density, quark nuggets wouldn't interact with light the way regular matter does, making them essentially invisible to us. But they would still have mass, and that's what would give them a gravitational pull.
Okay, that's pretty wild. But if these nuggets are so dense, wouldn't we have detected them by now? I mean, wouldn't they be colliding with regular matter and causing all sorts of chaos?
It's a good question, and it gets to the heart of why these are still theoretical objects. The thing is, even though they'd be incredibly dense, they'd also be incredibly small, meaning their chances of bumping into regular matter would be relatively low. But scientists are actively searching for any signs of these collisions, hoping to prove or disprove the quark nugget theory.
So the search is on, but what if dark matter isn't made of regular quarks at all?
That leads us to another intriguing possibility: dark quarks. These are hypothetical particles that share some similarities with regular quarks, but interact with a different set of forces.
So like quarks from a parallel universe.
It's a bit like that. They could exist alongside our familiar quarks, but only interact with them very weakly, potentially through some intermediary particle.
Okay, so how would we even begin to detect these dark quarks if they're interacting so weakly with our world?
That's where particle accelerators, like the Large Hadron Collider, come in. By smashing protons together at nearly the speed of light, scientists are hoping to create these dark quarks, even if just for a fleeting moment. It's like trying to smash open a piñata filled with subatomic particles and hoping something unexpected falls out.
I love that analogy. So we've got quark nuggets, dark quarks. It seems like physicists are getting pretty creative in their quest to explain dark matter. But I have a feeling we're just scratching the surface here, right?
Oh, absolutely. The theories we've talked about so far are just the tip of the iceberg. Your excerpts actually go much deeper, exploring ideas that delve into the very fabric of reality. Are you ready to get a little more mind-bending?
Bring it on. I'm ready to dive deeper into this rabbit hole.
Before the break, we talked about Quark Nuggets and dark quarks. But those are really just the first steps on this journey. The articles you sent us actually go way beyond those basic ideas.
Okay, I'm all ears. I love how these excerpts seem to build on each other, starting with familiar concepts and then leading us to some really mind-blowing possibilities. What's next on the agenda?
Well, we have to talk about something called supersymmetry, or SUSY for short. It's a theory that suggests a whole new set of particles are out there, waiting to be discovered.
A whole new set, like a secret mirror image of the particles we already know about.
Exactly. Imagine every particle we know, electrons, quarks, even the Higgs boson, has a secret twin, a superpartner particle. That's what SUSY predicts.
So like a whole other set of Legos to build the universe with. I'm trying to imagine what these superpartner particles would be like. Do they have superpowers?
No, not exactly superpowers, but they would have different properties than their known counterparts. And one of these hypothetical superpartners, called the neutralino, is considered a prime candidate for dark matter.
Okay, what makes the neutralino so special in the world of dark matter?
For one, it's thought to be stable, meaning it doesn't decay into other particles. It also interacts very weakly with regular matter, kind of like those dark quarks we talked about earlier.
So it's like a stealthy, invisible particle just floating around, exerting its gravitational influence, but not really interacting with the world we see. That does sound like a good fit for dark matter.
Exactly. But there's more to SUSY than just explaining dark matter. It's a framework that could potentially solve several other mysteries in physics. For example, it could help unify the forces of nature or provide insights into the hierarchy problem, why the force of gravity is so much weaker than the other fundamental forces.
So SUSY is a big deal, with implications far beyond just explaining dark matter. Okay, before my brain explodes from information overload, what's the next theory in this cosmic lineup?
Another intriguing idea is called technicolor. This one tries to explain the origin of mass in a way that goes beyond the Higgs boson.
Hold on, remind me again. What's the Higgs boson and why is it important?
The Higgs boson is a particle that gives other particles their mass. It's like the universe's mass-giving machine. But Technicolor proposes that there might be a whole new force at work, even stronger than the strong force. That binds together new types of particles called techniquarks.
Techniquarks. Are those like quarks but with even more technicolor?
You got it. And the idea is that these techniquarks could be the real source of mass for other particles, potentially even explaining the existence of dark matter. It's like saying the Higgs boson is just a middleman, and the real heavy lifting is being done by these techniquarks behind the scenes.
Okay, so Technicolor is a pretty radical departure from our current understanding of how particles get their mass. It's like rewriting the rule book of particle physics.
It is, and that's what makes it so intriguing. It's a reminder that there's still so much we don't know about the universe, and the answers might be far stranger than we imagine.
So we've got supersymmetry with its superpartners, and Technicolor with its techniquarks. Is there any theory out there that keeps things a little closer to the world of quarks as we know them?
Well, there's the idea of composite dark matter. This theory suggests that dark matter isn't made up of individual fundamental particles, but rather composite particles, kind of like how protons and neutrons are made up of quarks.
So instead of thinking of dark matter as a single mysterious particle, we could imagine it being made of smaller building blocks that combine in different ways, kind of like dark matter molecules.
That's the idea.
Yeah.
And this opens up a whole new realm of possibilities. For example, some models propose the existence of a mirror dark matter sector.
Mirror dark matter, so like a whole other universe made of dark matter mirroring our own, but invisible to us.
It sounds crazy, I know, but it's a serious possibility that physicists are exploring. Imagine a universe where there's a mirror version of every particle we know, a mirror electron, a mirror proton, even mirror quarks.
So I could have a dark matter doppelganger out there somewhere.
Maybe. But here's the catch. This mirror sector would interact with our world, only very weakly, perhaps through gravity or some other force we haven't discovered yet.
Okay, my mind is officially blown. These theories are getting wilder and wilder. But I have to ask, how do scientists actually go about testing these ideas? I mean, we're talking about particles and forces that we've never seen before.
That's where the experimental side of things comes in. Physicists are using some incredibly clever techniques to try and catch dark matter in the act.
Right. We touched on direct and indirect detection earlier. Can you remind me how those work?
Direct detection is like setting a trap for dark matter particles. Scientists build incredibly sensitive detectors, often deep underground. to shield them from cosmic rays, and wait for a dark matter particle to bump into an atom in the detector. It's a bit like listening for a faint whisper in a noisy room.
And what about indirect detection?
Indirect detection is more like looking for the aftermath of a dark matter interaction. For example, if two dark matter particles collide and annihilate each other, they might produce other particles that we can detect, like gamma rays or neutrinos.
So it's like looking for the smoke signals from a dark matter campfire?
A great analogy. And there are specialized telescopes in space, like the Fermi Gamma Ray Space Telescope, that are scanning the sky for these telltale signs of dark matter interactions.
Okay, so we've got these incredible detectors searching for dark matter particles directly, and telescopes looking for their indirect signatures, but it sounds like there's even more to the experimental side of things.
Absolutely. There are experiments dedicated to searching for specific types of dark matter particles, like axion.
Wait, axions, those were mentioned in your excerpts. Aren't those the hypothetical particles predicted by quantum chromodynamics or QCD? I remember the name, but honestly, that whole section was a bit over my head.
It is a complex theory.
Yeah.
But essentially, QCD is the theory that describes how quarks interact with each other through the strong force. And it turns out that QCD predicts the existence of all sorts of exotic particles, including axions.
So these axions aren't just your everyday quarks. There's something entirely new that arises from the way quarks interact with each other.
Exactly. And what's really interesting about axions is that they could solve several mysteries in physics at once. Not only could they be the answer to the dark matter puzzle, but they could also explain why the strong force behaves the way it does, which is something that has puzzled physicists for a long time.
So it's like finding a missing puzzle piece that fits perfectly in multiple places. That's pretty incredible.
It is.
Yeah.
And there are dedicated experiments, like ADMX and KKST, that are using very clever techniques to try and detect these elusive axions.
This is fascinating stuff. We've gone from basic quarks to superpartners, techniquarks, and now axions. It seems like physicists are pulling out all the stops to uncover the secrets of dark matter. But I'm curious, with all these theories and experiments, how do scientists even begin to make sense of all the data? I mean, we're talking about massive amounts of information, right?
You're absolutely right.
Yeah.
And that's where the power of computation comes in. Scientists are using powerful computers to create simulations of the universe, trying to model the behavior of dark matter and see how it influences the formation of galaxies and clusters of galaxies.
So like creating a virtual universe inside a computer.
Exactly. And these simulations can be incredibly detailed, tracking the movements of billions of dark matter particles over billions of years. One example is the Illustris TNG simulation, which has produced some of the most stunning visualizations of the cosmos we've ever seen, showing how dark matter acts as a kind of invisible scaffolding. That shapes the large-scale structure of the universe.
That's amazing. It's like watching the universe evolve before our very eyes, even the parts we can't see directly.
It is. And it's not just about simulations. Scientists are also using machine learning algorithms to analyze data from experiments and simulations, helping them find patterns and anomalies that might point to the existence of dark matter.
So it's like having a digital detective sifting through mountains of data to find those crucial clues.
Precisely. Machine learning is proving to be an incredibly powerful tool in the hunt for dark matter. It can help us make sense of the incredible complexity of the problem and guide future research efforts.
This is mind-blowing stuff. It feels like we're on the cusp of some major breakthroughs in our understanding of the universe. I can't wait to see what the future holds for dark matter research.
Me too. There are so many exciting developments on the horizon, from new particle colliders to next-generation space telescopes. And I have a feeling that the answers to the dark matter puzzle might be even more surprising than we can imagine.
I'm on the edge of my seat. Before we dive into the future of this field, let's take a quick pause to let all this amazing information sink in. When we come back, we'll explore what lies ahead for dark matter research and contemplate the incredible discoveries that might await us. Don't go anywhere.
Welcome back to the deep dive. I don't know about you, but after that last segment, I'm feeling like we've traveled to the edge of the universe and back.
It's amazing how these theories push the boundaries of what we thought was possible. We started this deep dive by talking about quarks, these tiny building blocks of matter. And now we're contemplating mirror universes and dark matter molecules. The excerpts he sent us have really taken us on a journey, but it sounds like the adventure isn't over yet. There's still so much to learn about dark matter and its role in the universe.
Absolutely. And the future of this field is incredibly exciting. There are all sorts of new tools and techniques being developed that could help us finally unlock the secrets of dark matter.
So what's on the horizon? What can we look forward to in the coming years?
Well, one of the most exciting developments is the possibility of building new, even more powerful particle colliders. We talked about a Large Hadron Collider earlier, but there are plans for even larger and more energetic colliders, like the Future Circular Collider, or the International Linear Collider.
So like the LHD on steroids.
Exactly. These future colliders would be able to smash particles together with such incredible energy that they might actually create dark matter particles directly. It would be like opening a window into the dark sector and finally being able to see what's inside.
That's mind-boggling. But it's not just about particle colliders, right? I remember our sources mentioned some amazing new space telescopes as well.
Right. The Nancy Grace Roman Space Telescope and the Euclid Space Telescope are both scheduled to launch in the coming years. These telescopes will be able to map the distribution of dark matter across the universe with unprecedented precision.
So we'll be able to create like a 3D map of where all the dark matter is hiding. That's incredible.
It is. And by studying how dark matter is distributed, we can learn more about its properties and how it influences the formation of galaxies and galaxy clusters. It will be like having a new set of eyes to observe the universe.
It sounds like these new tools will give us a much clearer picture of dark matter. But I have a feeling that solving this cosmic mystery will require more than just bigger machines and better telescopes. What else is happening in the world of dark matter research?
You're absolutely right. This isn't just about building bigger and better tools. It's about collaboration and bringing together the brightest minds from different fields of science. Initiatives like the Quantum Universe Initiative are doing just that, fostering collaborations between particle physicists, astrophysicists, cosmologists, computer scientists, and even quantum information scientists.
So it's a true team effort, a scientific all-star team, coming together to tackle one of the biggest mysteries in the universe.
Exactly. By combining expertise from different areas, we can approach the problem from multiple angles and develop new and innovative solutions. It's like putting together a puzzle. But instead of just looking at the pieces, we're also studying the box, the table it's on, and even the room we're in.
That's a great analogy. So we've talked about some of the amazing advancements happening in dark matter research. But I have to ask, after going through all these excerpts, is there anything that's really stuck with you? Any particular theory that you find especially compelling? Or any big questions that keep you up at night?
You know, as fascinating as all these theories are, and some of them are truly mind-boggling, I keep coming back to a fundamental question. What if dark matter isn't a new particle at all? What if it's something even more fundamental, like a modification to our understanding of gravity?
Wait, you're saying that maybe gravity doesn't work the way we think it does in certain parts of the universe?
It's a possibility that some physicists are seriously considering. Maybe on the largest scales, the way galaxies move and interact, our current theory of gravity breaks down. And maybe what we attribute to dark matter is actually just a manifestation of this modified gravity.
Whoa, that's a huge paradigm shift. It's like saying we've been looking for a missing piece of the puzzle when the problem is actually with the puzzle board itself.
Exactly, and it highlights just how much we still don't know about the universe. We may be on the verge of a revolution in our understanding of gravity, and that could have profound implications for everything, from cosmology to our understanding of the fundamental laws of physics.
This has been such an incredible journey. We've explored so many fascinating ideas, from the tiniest quarks to the grandest scales of the universe. And the excerpts you sent us have been a fantastic guide.
It's been a real deep dive into the heart of the matter, both literally and figuratively.
And the best part is, this is just the beginning. There's so much more to discover, so many more questions to ask.
I completely agree. This is an incredibly dynamic field, and I can't wait to see what breakthroughs the future holds.
Well, that wraps up our deep dive into the world of quarks and dark matter, curated just for you. Remember, this is just the tip of the iceberg. Keep exploring, keep asking questions, and who knows, maybe someday you'll be the one making the next big discovery in this field. Thanks for joining us on The Deep Dive.